We're now going to learn how to solve a system of linear equations. So this is a system of several simultaneous equations. So in general, we could have something like a1x1 plus a2x2 plus all the way up to anxn equals b1. And then maybe, in fact, if I call them a11, a12, a1n, then I could have a12x1 plus a22x2 plus a2nxn equals b2, all the way down to an1x1 plus an2x2 plus annxn equals bn. Okay, so that's quite complicated. Just to be clear, the xi's are the variables, and the ai and bi, or the aij and bi are constants. And we want to solve this system of n simultaneous equations to find the solution x1 up to xn, what each of these xi's are equal to. So we can write it as a matrix. We can write it as a matrix times x1 all the way down to xn equals b1 all the way down to bn. And then we have a11, a12 all the way to a1n, a21, a22 all the way to a2n, all the way down to an1, all the way down to ann, and the whole matrix is filled with the aij's. If I now call this matrix A, if I call this x and this b, x and b are vectors, so we have ax equals b, how can we solve this to find x? Well, if A is invertible, so if A is non-singular, if its determinant is non-zero, we can apply the inverse matrix to both sides. And then we just have to do A inverse times B. This is the solution. So to solve a system of n simultaneous equations, we can just use this formula. Now, you might ask, what if the determinant of A is 0? The answer is not so nice, unfortunately. The problem is, if you have a matrix like this, so if our equations are, let's say we just have two variables, and we have the equations x plus y equals 0, x plus y equals 0. And we have the matrix then 1, 1, 1, 1, xy equals 0, 0. The problem is, this matrix here has determinant 0. So we can't apply A inverse, and of course, because the two equations are the same, we get infinitely many solutions. Every pair, A comma minus A, is a solution. xy equals A comma, so things like 1 comma minus 1 or 3 comma minus 3 and so on are all solutions to this system. So the determinant of A is 0, that doesn't tell you. It might have infinitely many solutions, it might not have any solutions at all. So it's less clear-cut. In general for us though, so the key thing to remember, the key thing to know is this. If you have a system, so A is a matrix here, x is a vector, it's the thing we want to find, B is a vector, then you can apply A inverse to both sides if the determinant is non-zero. So in general, you'll just use your calculator to find A inverse. If we have something like this, so if we have a system of three equations, minus x plus 6y minus 2z is 21, 6x minus 2y minus z is minus 16, and minus 2x plus 3y plus 5z is 24, then we can write this as a matrix times x, y, z. So what is the matrix going to be? Well, to make the this bit, we're going to need to have minus 1, a lot of x, plus 6, lots of y, minus 2, z. And similarly for the other two equations, and we get this matrix. And then we can find the inverse using a calculator and multiply both sides by the inverse matrix to give x, y, z is this matrix inverse times 21 minus 16, 24, and that just gives us minus 1, 4, 2. So this tells us the only solution to this system of equations is x is minus 1, y is 4, z is 2. Now, of course, you can also solve three simultaneous equations by hand, eliminating an unknown. For example, you could double this second equation and then subtract the first and modified second equation, but it's much easier to use the matrix method. So there's no need to find the inverse by hand unless it involves an entry that has an unknown in it, like k. Okay, we're now going to look at an example that involves modeling, because there have been some very difficult modeling questions about systems of linear equations. So let's consider this example. A sheep farmer has Hampshire, Dorset horn, and Wiltshire horn sheep. So three types of sheep. Initially, her flock has 2,500 sheep. There were 300 more Hampshire, or rather had 2,500 sheep. There were 300 more Hampshire than Wiltshire horn. After 1 year, the number of Hampshire increased by 6%. The number of Dorset horn increased by 4%. The number of Wiltshire horn increased by 3%. And the total flock size increased by 110. And the question is, find out how many of each type of sheep were in the initial flock. Okay, so this is a very standard kind of question about this topic. So we need to form a matrix equation. We need to form a system of linear equations. So if I let H be the number of Hampshire initially, D be the number of Dorset horn, and W be the number of Wiltshire horn initially, then we know initially there were 2,500 in total. So what does that tell us? It tells us that H plus D plus W is 2,500. We also know there were 300 more Hampshire than Wiltshire horn. That tells us H is W plus 300, or H minus W is 300. So H minus W is 300. And we know after 1 year we have all this extra information, which we can use to form another equation, because we know after 1 year we're going to have, well, the flock has increased by 110, so it's up to 2,610. Hampshire have increased by 6%, so we can multiply by 1.06. Dorset Horn have increased by 4%, so that's 1.04D. And Wiltshire Horn have increased by 3%, so that's 1.03W. And now we can form a matrix equation. We've got this matrix 1, 1, 1, 1, 0, minus 1. It's a 0 because there are no D in this second equation. And 1.06, 1.04, 1.03 times HDW equals 2,500, 300, 2,610. And now we can apply the inverse matrix to both sides to give us HDW is this matrix inverse times 2,500, 300, 2,610. And then you just stick this in your calculator and it will give you the answer. So we should get an answer of 700, 1,400, 400. So we can say initially there were 700 Hampshire sheep, 1,400 Dorset Horn, and 400 Wiltshire Horn. And that's the answer. Note that if you had something like one of these things had decreased rather than increased, for example, if Wiltshire Horn decreased by 3%, instead of 1.03, we would use 0.97. Okay, yeah, so that's a standard method you need to be familiar with. Next, we state a definition. A system of linear equations is called consistent if it has a solution, and inconsistent otherwise. So inconsistent means it has no solutions. Okay, so that's just what consistent and inconsistent mean. A fact, which we'll talk more about later in chapter 9, is that we already know if we have ax plus by plus c equals 0, this is the equation of a line in the plane, the xy plane. Line, like that. If we have ax plus by plus cz plus d equals 0, what is this? Well, I can tell you it's not a line. This is in fact a plane. So if you have 3 axes like this, then the equation ax plus by plus cz describes a plane. A plane is an infinite two-dimensional space. So extending infinitely. So for example, the xy plane that we're sort of, or the YZ plane, this is the plane where x is 0. So if you think about the x-axis as coming out of the screen itself is then the YZ plane. So anyway, all we need to know is this ax plus by plus cz equals plus d equals 0 describes a plane. We don't need to worry too much about that for now, but about why this is true for now, because we're going to see it in chapter 9. But the reason this is important for now is we can see in these examples of linear systems, each of these equations describes a plane in 3D. So we have 3 planes. And these 3 planes in this sheep example met at this point, 700, 1,400, 400. So we can have different configurations of planes that we're going to use to solve, well, we're going to interpret geometrically solutions to systems of linear equations. So there are various different possibilities. First, there are the consistent cases. I encourage you to have a look at page 118 of the book, because the diagrams they have there are probably much better than I can draw. So the first consistent case is that three planes meet in a point. So if we have three planes, so I'll draw one in blue like this. If we have a different plane, I'll draw in green. So you can see it's going behind. Maybe I should I'll draw in dash what we won't see because it's behind the there we go. So the green is a second plane, and we can see these two planes meet in this line. Whoops. Meet in this yellow line here. That's the line these two planes meet in. Okay, and then if we have a red plane, that's going to be here. And we can see these three planes are going to meet in this point where the red dot is. Somewhere along where the red plane meets the yellow line. So this is what it looks like geometrically for three planes to meet in a point. Obviously, this isn't the only thing it could look like, but this is just one illustration. Okay, case two. We could have three planes that form a sheaf. A sheaf. So this is a bit like if you open a book and fan the pages so that they kind of all spread out, but they're all connected by the spine of the book. So so if we start with a red plane like this, and then if I draw a blue plane like this, that is in front on this side, but then is behind down here. And then if I draw a green plane like this, and then it goes behind here, and then we can see this black line here, is where these three planes meet. They meet in a line. This line is called a sheaf. Sorry, the three planes are said to form a sheaf. So here, they meet in a point. There's only one solution to the system of equations. Here, there are infinitely many solutions, all on this line. And then the third consistent case... no, there's not a third consistent... Yes, the third consistent case is that two or more of the planes are the same plane. So, in fact, you could have that they're all the same. So, in fact, we saw that somewhere in an example. Right, yes, this example here. Here, we had that the two equations were the same. So, when that happens, okay, in that case, it was only two equations, so they form the same line. So I should really say we're specifically interested when we're talking about these consistent cases in systems of three linear equations. Three linear simultaneous equations. Yeah, so the third case is the case where the planes are the same. So if they're all the same, then every point of that plane is so here we just have one plane. They're all the same plane. Every point of the plane is a solution. So that's, again, infinitely many solutions. You can also have the case where two are the same plane, and then we have another plane, and then either, well, sometimes in that case there are no solutions because the two planes could then be parallel, but you could also have they meet in a line. Okay, so now on to the inconsistent cases. So number 4, so inconsistent, remember, means there aren't any solutions. So number 4, we could have that some of the planes are parallel. So what does it mean if we have planes that are parallel? Well, so here's a red plane, and if I draw behind it, a blue plane that's parallel, and then I could have another plane, doesn't matter what it looks like, the third plane can be anything we like. There are no solutions because there are no points that lie on both the red and blue planes at the same time. So the third plane could be anything. So I could draw it like this. It doesn't matter how I draw it, as I said, or maybe we'll just draw it like that. And then, yeah. So here, there are no solutions. The system is inconsistent. That's what inconsistent means, no solutions. 5. Last case, the planes form a prism. So in this case, we might have a blue plane like this, and then a green plane that is something like this. And then a red plane that is horizontal. I'll try and redraw this. Again, there's a picture on the book, page 118, which is probably better than I can draw. But the idea is now to have a red horizontal plane that doesn't intersect both the blue and green planes at the same time. So I'll just try again. So red plane here, blue plane here, and then green plane horizontal, but doesn't like this, and all three planes do not meet at any point. There's no point that lies on all three planes. So this again has no solutions. We need to determine which of these 5 types. You can be asked in the exam to work out which of these 5 types the system of linear simultaneous equations is. So the way the question is phrased is usually something like, give a geometric interpretation. So things like, give a geometric interpretation of the system of linear equations, or describe or identify the geometric configuration of planes, or something like this. So how do you know? Well, first of all, does it have a solution? If you solved it and you got one solution using the inverse matrix, you're definitely in the first case. So this case, the one solution is given by x equals a inverse b. If you couldn't do that, because, for example, the determinant is 0, you're in one of the other cases. So this case, the determinant of a is non-zero, a inverse exists. The planes are the same if their equations are the same. I mean, possibly you could have something like this. These are the same. If you divide the second one by 2, you get the first one. So these are the same plane. The equations will either be the same or multiples of each other. So that's how you know if the planes are the same. And then lastly, they form a sheaf if they're not the same, but you have infinitely many solutions. And then onto the inconsistent cases, you'll know if planes are parallel because when we have something like, well, first of all, just think about the planes x equals 0 and x equals 1. These are parallel. One of them is, so again, if the x-axis is coming out of the screen, one of them, so x equals 0, that's the screen itself. X equals 1 is parallel and lifted a distance 1 up from the screen. So planes like this are parallel. In general, planes like ax plus by plus cz plus d and ax plus by plus cz plus e are parallel. So if you have two equations like this, you're in this case. And you have no solutions, assuming they're not all three the same. If the planes form a prism, well, that's if there are no solutions and you don't have that two of the planes are parallel, you're in this last case. Okay, so now let's look at an example. So consider the system given by the three equations 3x minus ky minus 6z equals k, kx plus 3y plus 3z equals 2, minus 3x minus y plus 3z equals minus 2. And the question is, in each case, is the system consistent or not? How many solutions are there? And what is the geometric interpretation? So there are three things to do for each case, but we'll just, okay, in case, the first case is k is 0, the second case is k is 1, the third case is k is minus 6. So, in the case k is 0, we can replace everywhere k appears here with a 0. We want to know which of these cases we're in. The first thing to check is whether the determinant is 0 or not. Because if we know that, we know immediately if we're in this case 1 or not. So, that's really the first thing to check. Your calculator can easily work out the determinant of the matrix in the case k is 0, and your calculator will find this is minus 18. This is non-zero, so that immediately tells us we're in case 1. Therefore, the system is consistent. There is one solution, and the geometric interpretation is the planes meet in a point. Done. Okay, B. K is 1. So again, the best thing to check first is what is the determinant of the matrix. So we have now 3 minus 1 minus 6, 1, 3, 3, minus 3 minus 1, 3. Well, I can see... Yeah, so in this case, the determinant is going to be 0, which is bad news because it means we're not in that first case. So we have many other cases to consider. So let's actually just write down the system of equations that we've got. So that's the system. What we want to do now is we want to try and figure out which of these might apply. So a sensible thing to think about might be, are any of the planes parallel? Are any of the planes the same? And if not, that eliminates cases 3 and 4. So then we don't have much left. So we'll just start by looking, are any of them parallel? Probably doesn't take too much thinking about to see no, they're not. None of them are parallel. So we couldn't possibly be in those cases. So are there any solutions or not? Do they form a prism or do they form a sheaf? Let's see. Well, I mean, one way, if you find a solution, you're done. You can say it's a sheaf now. But how could we go about looking for solutions? Well, we could try and eliminate now a variable. So if I call these equations 1, 2, and 3, let's try and eliminate z. So let's do 2 minus 3, which gives us 4x plus 4y equals 4. And now let's eliminate z from number 1. So let's do number 1 plus 2 times number 2. So we're going to get 5x plus 5y plus no z equals 5. Both of these give us x plus y equals 1. So there are infinitely many solutions. In fact, any solution of this equation with an appropriate value of z is then a solution. So there are, in this case, there are infinitely many solutions. The system is consistent, and the planes form a sheaf. Now, you might wonder what would happen differently if they didn't form a sheaf. What if it was a prism instead? What you would end up with at this stage is we might have something like 5x plus 5y equals 9. And then the two simultaneous equations with just x and y can't be solved, because it's impossible for x plus y to be 1 at the same time it's 9/5. So if you end up with a contradiction like that, they form a prism. Okay, and then lastly, the case where k is minus 6, so this is part C. In this case, let's first work out the determinant again. So we now have the determinant of 3, 6, minus 6, minus 6, 3, 3, minus 3, minus 1, 3. Your calculator can find this, it'll find it 0. So we're not in case 1. So let's do the same thing again with the equations. So we've got this is minus 6. We've got minus 6x plus 3y plus 3z is 2. And we've got minus 3x minus y plus 3z is minus 2. Let's again call them 1, 2, 3. Well, now, are any of them parallel? No, they're not, because the thing on the left, remember, has to be a multiple of one of the other things on the left for the planes to be parallel, or the same plane. So that doesn't happen anywhere here, so no, that doesn't happen. So that narrows it down again to either a sheaf or a prism. So let's do the same thing we did before. Let's eliminate something. We could eliminate z again, but I think let's eliminate z again. So if we do 2 minus 3, we get minus 3x plus 4y equals 4. And if we eliminate z from number 1, so if we do 1 plus 2 times number 2 again, we get minus 9x plus 12y equals minus 2. And then let's divide this fifth. So if I call this number 4, number 5, if I divide the fifth equation by 3, I get minus 3x plus 4y equals minus 2/3. So now look very closely at the two equations in the blue boxes. These are not consistent. It's impossible to have value of x and y that satisfy both of these two equations at the same time. Can't happen. So therefore, no solutions. the system is inconsistent and the planes must form a prism. They couldn't form a, we couldn't have that some of the planes are parallel because we saw none of them are parallel. They have to form a prism. And we're done.